String theory is a complex and fascinating way of describing the universe, but one that can give people headaches to try to figure out. Nonetheless, it can be understood and without a lot of math. So, grab your coffee and your Tylenol as we seek to unravel the secrets of the universe. Today we're looking at string theory along with its many variants. Our goal is to explain it in a detailed and nuanced way, without resorting to the usual simplifications found in popular science explanations, or at least to delve deeper into those analogies where necessary. A complete understanding does truly require advanced math, which we will even discuss a bit of today. But unless you're wanting to actually do calculations and particle physics yourself, I don't think that degree is needed, and I think we can bridge a lot more of the gap than most explanations usually do. I want to start with two big points up front. First, there's a tendency to assume we mean fundamental particles like electrons and quarks are built out of smaller strings, that they are the particles those bigger particles are made of. That is not the idea. It's not one yet smaller building block which might itself have smaller bits too. We are already at the bottom of reality. It's saying an electron is a string, vibrating in a standing wave, with certain properties that make it an electron, and a quark is a string, singular. So is any other fundamental particle, be it a neutrino or photon or muon or whatever. Whatever it is, muon or quark or whateverons, depends on how that string is said to vibrate. That's where the extra dimensions start coming in. But that's to make the math work out. You don't need to be able to wrap your head around 10 or 26 dimensions. Just understand that each string has a characteristic vibration that determines what particle or energy field it is. And these are mostly open strings vibrating between 2 points, a pair of D-branes, which are higher dimensional and which we will discuss later. It can seem confusing, but if instead of string I just said Lego block, and so they come in many forms, each a unique plastic block of a certain shape and color, that wouldn't seem that bizarre. But in quantum, stuff is characterized by fields and waves and energies, so a vibrating string between 2 points fits better. It's still an analogy though, not an actual string. The exception to that is the closed loop that is the graviton, and maybe a few others, the particle of the force of gravity, which isn't even supposed to exist in Einstein's general relativity. And at a fundamental level, this weird disconnect between general relativity and quantum mechanics, where gravity is concerned, is what string theory is intended to help with. That's the big two things about string theory. First, any fundamental particle can be represented by an open and vibrating string, or sometimes a closed loop of one, albeit with some extra and extra tiny dimensions to permit sufficient degrees of freedom for them to vibrate in. Second, string theory aims to mesh our understandings of quantum and general relativity, particularly around that weird animal that is gravity. That is it, and if you got that down, you've already gleaned more about it than I've tended to notice folks get after most discussions of string theory, which seems to summarize as, there's tiny vibrating strings everything is made of, and extra dimensions, which isn't wrong but tends to miss the point. And again, is that any fundamental particle, or universal Lego blocks, can be described as vibrating strings, and then the math for a lot of physics works out better, especially around some other weird animals like gravity and point-like objects. String theory is undeniably complex, and it's fair to say it sits on the cutting edge of both physics and our imaginations. It introduces ideas like extra dimensions and non-intuitive concepts, but we will aim to unravel it as best we can. A quick summary of string theory is that it tries to address certain fundamental problems in the standard model of particle physics, particularly the notion that the most basic building blocks, such as quarks and electrons, are considered point-like particles with no size. This raises a question: how can something with no size exist, and how can something that is infinitely tiny interact with other particles or forces? How does gravity, a force that acts on objects with mass, fit into a framework that treats fundamental particles as having no internal structure? They're just an infinitely tiny dot. For instance, if an object, no matter how tiny in mass, is point-like, then it is infinitely dense, and that means it is smaller than its own Schwarzschild radius, how wide something of a given mass can be without being a black hole. We have some workarounds for that, including the uncertainty principle, And indeed, we have theories that treat particles as black holes too, or singularities, but it's an example of how problematic a point-like particle can be. String theory offers a potential solution by suggesting these particles aren't point-like at all, but are instead made up of tiny, one-dimensional strings that vibrate at specific frequencies, and that passes through many dimensions, the same as a normal 1D string might pass through 3. The way a string vibrates determines the properties of the particle it represents, such as mass, charge, and spin. The challenge here is that we have a ton more properties, like the various quantum numbers we will discuss later, and the mathematics of string theory only works if we introduce extra dimensions. In the simplest form of the theory, we are talking about 3 familiar spatial dimensions, plus time, plus 6 more dimensions that are compactified, so small that we don't perceive them in everyday life, and indeed a lot smaller than an atomic nucleus. M-theory, a more developed version of string theory, takes these things even further by adding yet another dimension, bringing the total to 11. This is where most explanations of string theory stop, and it's also where string theory starts to diverge into different versions. Today we'll explore these versions in some detail, obviously not a lot, but I also want to mention my own perspective as a disclaimer. I am personally not a fan of string theory, though I'll try to keep my biases in check and have a friend, Jonathan Maltz, who knows the topic much better, help me on the script. My distaste stems more from metaphysical discomfort than scientific objections. I appreciate the elegance of string theory's mathematics and the problems it seeks to solve. However, I'm wary of its reliance on concepts like extra dimensions, and I think it's worth acknowledging that many physicists share similar reservations. That includes a lot of its proponents too. They are wholly unaware of this problem or trying to sweep it under the rug. Despite the media's portrayal of string theory as the next big thing in physics, it is not new, and opinions within the scientific community are divided. Most physicists work in areas far more removed from string theory, and thus often have no firm opinion on it, and those who do have opinions are split. Some think string theory is a promising path forward, while others are more skeptical. Many are both simultaneously, like a particle and a wave. As we'll see today, there is a lot going for the theory, but also a lot going against it. One major sticking point is the difficulty in finding empirical evidence for string theory. This isn't limited to string theory either. Quantum gravity and a host of other cosmological theories suffer from evidence being hard, if not actually impossible, to acquire. It's not that physicists aren't trying, it's just that string theory operates at scales that are far beyond our current ability to measure. To understand why string theory was proposed in the first place, and the better part of a century ago, we need to consider not only the basic concept of the theory, but also its historical context. If we think of the progression of scientific discovery, it seems natural that after discovering cells, organelles, molecules, then atoms, and then subatomic particles like protons, neutrons, and electrons, we would eventually look for something yet smaller. All of these layers acted and looked very different from each other, but the earlier planetary model of the atom tended to make folks think each layer was just a miniature version of the last, and that might go on ad infinitum. And after all, you can always cut a number in half again, no matter how small each successive piece is. But the science was looking otherwise, and while the gun got jumped by naming atoms such, atom is Greek for indivisible but could be divided into electrons, protons, and neutrons, the end of the race for a fundamental building block was seemingly in sight. And indeed, the electron is a fundamental particle to the best of our knowledge, and string theory does not say otherwise. It just says it's a particular type of string. The proposal of quarks in the 1960s gave us another layer of understanding, and so it is reasonable for most people to assume that we could keep finding smaller and smaller building blocks. But again, the situation in physics at that time was more complex than this Matryoshka, Russian doll view of matter might suggest. Quantum mechanics, the theory that describes the behavior of particles on the smallest scale, has already revealed that the universe doesn't work like the smooth, continuous world of classical physics. Instead, things happen in discrete steps or quanta. For instance, protons always have the same mass, and electrons always have the same charge. There are no partial electrons or slightly heavier protons. This discreteness, having only one value or a short handful of them, not a spectrum, is one of the core principles of quantum mechanics. So when quarks were proposed as the building blocks of protons and neutrons, It wasn't just a matter of dividing particles into smaller pieces. We suspected we were already at the bottom or close for fundamental particles. Physicists weren't expecting to find an infinite series of smaller and smaller building blocks, but they were still looking for a more fundamental layer of reality that could explain the behavior of these particles in a way that aligned with quantum mechanics. This is the central idea behind string theory. It proposes that beneath the level of quarks and electrons, the universe is not made up of particles at all, but of tiny vibrating strings. These strings are not sub-quarks or sub-electrons. They are fundamental objects in their own right, that come in types, and those quarks and electrons are those types. The vibrations of the strings determine the properties of the particles we observe, such as their mass, charge, and spin. This approach avoids some of the conceptual problems of point-like particles, particularly the issue of infinite density, which we'll explore in more detail shortly. The notion that particles like quarks and electrons are point-like creates several theoretical problems. One of the most significant issues is that a point-like object with a finite amount of energy, no matter how small, should theoretically collapse into a black hole. This is because, according to general relativity, any object with mass has a Schwarzschild radius, a distance beyond which the gravitational pull of the object becomes so strong that not even light can escape. For a particle as small as an electron, the Schwarzschild radius would be much smaller than anything we can currently observe, but the concept still poses a problem. To make matters worse, the standard model treats particles like electrons as having no internal structure. Experimental evidence suggests that if electrons do have an internal structure, it's smaller than a billionth of a nanometer. By comparison, protons have a measurable size around 1600 to 1700 atometers. An atometer is 1 billionth of a nanometer, 10 to the negative 18th meters. This measurement creates a paradox. If electrons are point-like, they should have infinite density and collapse into black holes, and ones that, according to Stephen Hawking, should near instantly evaporate, yet we don't see either of those things happening. One possible explanation involves the uncertainty principle, which smears out the location of a particle over a wider area than its Schwarzschild radius, preventing it from collapsing into a singularity. Today we're exploring the mysteries of string theory, a framework that seeks to unravel the very fabric of this universe, and maybe many more. And if you're looking for another fun mystery, check out Faithless, a Sojourn story, a feature-length audio drama. Follow Castian Vadric, a former Inquisitor turned fugitive heretic, as he journeys through the Sanctum to uncover ancient truths and reunite with his beloved Valendra. Faithless is a captivating chapter in the award-winning The Sojourn series and a one-of-a-kind audio cinematic experience reminiscent of The Expanse. That's out now along with this month's SFAA monthly exclusive, The Fermi Paradox Air, where we investigate how planetary atmospheres may act as filters that shape the emergence of life on alien planets, and if we can grow to intelligent life that might sojourn out to the stars. To see those monthly SFIA exclusives along with every episode of SFIA a few days early and ad-free, sign up now to Nebula at go.nebula.tv/IsaacArthur, using my code IsaacArthur to get 40% off an annual membership. That's less than $3 a month. Nebula also offers lifetime memberships and gift cards, so you can share incredible content like Faithless and SFIA's exclusive episodes with friends and family. And now, let's get back to untangling string theory. String theory offers a different solution. Instead of treating particles as point-like objects, string theory proposes that they are one-dimensional strings with a finite length. These strings vibrate at specific frequencies. The way they vibrate, again, determines the properties of the particles they represent. This approach sidesteps the issue of infinite density because the strings have a finite size, even though they are incredibly small, on an order of a Planck length, which is about 1.6 times 10 to the negative 35 meters, a billion times smaller than a proton. String theory was first developed in the late 1960s and early 1970s as an attempt to explain the strong nuclear force, which holds protons and neutrons together in the nucleus of an atom. Around this time, physicist Murray Gell-Mann had posited that protons and neutrons were made up of smaller particles called quarks, and that quarks were held together by particles called gluons, which mediate or transmit the strong force. The strong force is incredibly powerful, hence the name, but operates only over very short distances, on the order of a femtometer, 1/400,000th of a meter. Early versions of string theory were aimed at explaining this strong force, but they struggled to account for certain experimental results. By the late 1970s, string theory had fallen out of favor, largely because every formulation contained something that looked a lot like a graviton. Gravitons are problematic in physics, and quantum chromodynamics, QCD, was emerging as the dominant theory of the strong force, so pushed early string theory aside. This was also the period where bosonic string theory was the primary theory, and it is the one with 26 dimensions to it. It is interesting to see references to it in science fiction by period. String theory was revived in the 1980s, partially as a means of explaining gravity in quantum theory, or quantum gravity, and this meshes with talk of grand unified theories of everything, and this sometimes is called the first superstring revolution. During this period, physicists developed several different versions of string theory, each with its own unique features. This included Type 1, Type 2, A and B, and heterotic string theories. In some versions, the strings were closed as a loop or open, meaning they had two distinct endpoints. In these versions, which are the more common ones, any given particle will either be closed or open, and which are which do vary. In some versions, strings are just closed. Closed strings are particularly noteworthy because they can be used to describe gravity. The graviton, the hypothetical particle that mediates the force of gravity, is thought to be a closed string, and the other gauge bosons that transmit forces are described this way in some versions of string, and open in others. This can't really be explained without dipping very deep into the math of each case, but it references a key point. String theory isn't really all that focused on strings themselves. They are just one piece of the puzzle. And they are just an analogy mostly derived from how quarks seem to be glued together or connected by a tube or string. The various ways a string vibrates in its various extra dimensions of freedom tells us its properties as particles. As string theory continued to evolve, it became clear that the theory required more than just three familiar dimensions of space and the one dimension of time. To make the mathematics of string theory work, physicists had to introduce extra dimensions, largely because of the Veil anomaly, which we'll touch on in a minute. In most versions of string theory, there are 6 extra spatial dimensions, making a total of 10 dimensions when we include time. These extra dimensions are thought to be compactified, meaning they are curled up so tightly that they are undetectable at all scale. The introduction of extra dimensions is one of the most mind-bending aspects of string theory, and as I've already indicated, I tend to feel like it serves as an unnecessary roadblock to people understanding the idea, as I feel like we need them for the true theory but can bypass them for casual explanations. At first glance, it seems counterintuitive to think there could be more than 3 dimensions of space. After all, we experience the world in 3 dimensions, length, width, and height. But in string theory, these extra dimensions are necessary to explain the behaviors of strings, up, down, left, right, etc. If you are curious, we sometimes use ana and kata for discussing direction in a 4th physical dimension. Much of the need for extra dimensions comes from the Veil anomaly. This happens when a quantum system breaks a symmetry called scale invariance, where the laws of physics shouldn't change if you zoom in or out on space-time. Even though this symmetry exists in the original theory, tiny quantum effects cause it to fail when you do calculations. This failure shows up as energy behaving in ways that depend on the shape of space-time, making a key tool in studying curved space-time, black holes, and string theory. We also often get new emergent laws for systems as we zoom out to higher levels of reality. Psychology is built on biology, which is in turn built on chemistry, and that in turn on quantum. You don't need to understand those lower layers to make the higher layer understandable. They have their own emergent laws, but the rules of those lower layers still apply and work. The Veil anomaly, though, indicates that quantum might not work at higher levels, but adding some extra dimensions removes the Veil anomaly. To understand why extra dimensions are required without tons of high-level math, let's consider how strings vibrate. In 3-dimensional space, a string can only vibrate in a limited number of ways. It can move up and down, side to side, back and forth, or some combination of the above. But if we add extra dimensions, the string gains more freedom to vibrate in different ways. These additional degrees of freedom are crucial for explaining the wide variety of particles and forces we observe in nature. And again, this is not the only place we get this problem popping up. For example, in most versions of string theory there are 6 extra dimensions, which are compactified and hidden from view. These dimensions are thought to be curled up at a scale much smaller than the size of an atomic nucleus, and this is also called flux compactification. This is also where D-branes come in, and they can curl up in many different ways in these many compactified dimensions. Much as you can fold something in different directions by folding it up or down, left or right, or a combination thereof. Only we have more dimensions to mix and match here. Indeed, something like 10 to the 500 different ways, with each implying a different possible universe with different properties, which we'll return to later. Explanations of compact dimensions are usually when folks start talking about garden hoses or wires as an example of something that from far away looks one-dimensional but up close is 3D. If that works for you, fine. I think it's easier to note that not all dimensions run off to infinity. Angle is 0 to 360 degrees, for instance. You can plot almost anything as a dimension too, like plotting fruits on a 3D chart of their color, weight, and sweetness, none of which require infinity or physical dimension. Letters of the alphabet, unlike numbers, are discrete. In English they are 26, and there is no equivalent to 1.5 or a half, just A or B. There's no 1/3 of a C. There's nothing stopping a dimension from only having, say, 2 states, positive or negative, or only permitting discrete values of them like 1, 2, 3, or A, B, C. In a universe where you had only one physical dimension that was infinitely long, and 2 other dimensions that each only expanded to be 3 spots wide, like left, middle, and right for one, and up, center, and down for the other, you get a nearly 1D universe with a pair of compact ones perpendicular to it and each other. We might say left was positive charge and right was negative charge, and some weird thing called isospin was up or down, or maybe could have many values but all of them integers or halves. Though just as a heads up, while these exist for helping describe unique quantum numbers each particle has, which we'll return to in a bit, the various quantum numbers don't each have their own specific dimension. Dimension 5 isn't electric charge or 6 isospin, any more than our mundane Dimension 2 is speed, or Dimension 3 is momentum. We use the extra dimensions for making the math work in describing the particle or string's properties. They're not just non-physical dimensions labeled with those properties, which you can also do if you like, same as you might make a 5D chart listing a person's age, weight, gender, hair color, and religious denomination. Again, don't let the mention of extra dimensions scare you off trying to understand it. They don't all have the same number either. M-theory, one of the most advanced versions of string theory, adds yet another dimension, bringing the total to 11. In both 10D string theory and M-theory, strings are not free-floating but are attached to higher dimensional objects called branes. But M-theory introduces both M2 and M5 brane types, and only when you wrap the M2 brane around the circular direction do you go from 10 to 11 dimensions. In general, these branes, be they M-brane or D-brane, can be thought of as the endpoints of strings, what these one-dimensional strings are anchored to on each end, assuming they're not looped onto themselves into a closed string anyway. In this framework, gravity is a force that can propagate through all 11 dimensions, while the others are all stuck in 2 or 3, which may explain why gravity is so much weaker than the other fundamental forces. If gravity is leaking into these extra dimensions, its strength would be diluted in the 3 dimensions we experience. The existence of extra dimensions also opens up the possibility of a multiverse, and not specifically the kind with divergent timelines of what-ifs that's saturating science fiction these days. Rather, it's a collection of parallel universes, each with its own physical laws and constants. In M-theory, our universe could be a 3-dimensional brane embedded into a higher dimensional space. Other branes, representing other universes, could be floating nearby. If 2 branes were to collide, it might produce a cosmic event similar to the Big Bang, which presumably created our universe. In our multiverse episode, we explored a lot of the different multiverse theories and types, and one of those is out of string theory, and it results in different types of universes in the multiverse based on possible compactifications. This can give you the colliding branes option, or separate bubbles of different compactifications, which we think would have different standard models of physics, different particles, different force carriers, something beside quarks and electrons and gluons and photons. This isn't necessarily infinite, though it could be, in which case you'd also get the more standard multiverse of sci-fi where you have every possible timeline able to happen, only here it's just a different but similar universe where similar events unfolded, not a splitting of timelines into new universes. Again, see our multiverse episodes for more discussion of that, and our episode on the Library of Babel and Infinite Monkeys for more discussion of the numbers involved. In this case, the really big number you'll hear a lot is 10 to the 500 vacua, or vacuum states, and each vacua could be thought of as one possible universe with different properties. Some of these might permit life, some by evolution, some might only allow it by the ultra-low probability of a Boltzmann brane, that is a randomly assembled brane from particles just bouncing into each other, which is absurdly unlikely, but not nearly as improbable as 10 to the 500 is big. Plus it might be more likely in other places. There's no useful analogy for how big 10 to the 500 is. Even 10 to the 100 is trillions of times bigger than the number of atoms in our universe. And again, see that Library of Babel episode for discussion of truly huge numbers like this, and its impact on the Fermi paradox and the anthropic principle in our fine-tuned universe episode, both from last summer. One of the challenges of understanding particles in quantum mechanics is that they are described not only by their mass and charge, but also by a variety of quantum numbers that specify their properties. These quantum numbers include things like spin, isospin, color charge, and flavor, terms that don't all have direct analogies in the macroscopic world, even if the name might sound familiar. Some, indeed the original four, sometimes called the fundamental quantum numbers, popped up in the 1910s and 1920s and relate only to electrons. Others, relating to nuclear properties like isospin, come later and are what opened the door to string theory by trying to figure out how they related and how the strong nuclear force worked. Again, it is because the strong force is so strong and the way it behaves that we get the string analogy. The chromodynamic field lines are pulled to the valence quarks so much that they don't spread out like electric field lines, but form a tube connecting, for example connecting the two valence quarks in a meson. The chromoflux tube of QCD was the string-like object that the old string theory was describing, and what made it a seemingly good description of strong interactions. As a quick reminder, nucleons like protons and neutrons are said to be composed of 3 quarks each, but these are the valence quarks. And they are not all the quarks, similar to how only the outer shell of electrons on atoms, the valence electrons, are the only ones interacting with the world up at the chemical level. If you look at the mass of a proton or a neutron and then the mass of the up and down quarks, you'll see they only account for about 1% of the mass of that proton. The rest is in gluons, that binding force between those 3 valence quarks, and is said to be made of more Fermi or C quarks, which can include the other larger types of quarks. We talked about this more in the Antimatter Factories episode, but it is a reminder that the gluons, which are associated with the strong nuclear force, are truly enormous, especially compared to those quarks. In string theory, these quantum numbers correspond to different modes of vibration for strings. Just as a guitar string can produce different notes depending on how it's plucked, a fundamental string can produce different particles depending on how it vibrates in the extra dimensions. This is also how you get different masses. Different modes of the string will carry different amounts of energy. This provides a natural way to explain the wide variety of particles we observe, as well as their specific properties. For instance, the strong force, which holds quarks together to form protons and neutrons, involves a property called color charge. The names really don't mean much. In physics, we tend to need to name things to usefully study them without confusion, and generally we don't really understand them well at the time. Color and flavor do not exist at the nuclear level, so using them as labels wasn't likely to be too confusing. Not many people realize the terms charge and battery predate electronics and were borrowed from the field of artillery, or that battery is a term for the number of cannons in a company-level unit of artillery, because they battered at the enemy with volleys of fire, which has very little to do with the battery running the device you might be watching this on. So never think of quantum numbers with familiar-sounding names as being particularly meaningful. Isospin or isotopic spin or isobaric spin is related to baryons, things made of 3 quarks, though isospin predates the idea of quarks by a few decades. We just knew the proton and neutron had a quantity in common that was opposite, and which we labeled 1/2 and -1/2 respectively, and which some other particles had 0, or plus or minus 1 of, or even 3/2. We eventually realized the up and down quark each had half and -half of this isospin, and that could add up to make particles like the proton and neutron. Each of the other quark types has a flavor or quantum number, strangeness, charmness, topness, bottomness, all of which are meaningless names, but they needed a name to be usefully discussed. And we got more like weak isospin, baryon number, lepton number, parity, charge parity, color charge, hypercharge, weak hypercharge, and probably others I'm forgetting. And critically, they are all quantized values. They come in discrete bits, like the letters in the alphabet do, and we need them to clearly and totally describe particles, and this is what the extra dimensions are for, as if we think of each particle as a standing wave of a vibrating string, all the different tiny dimensions give it different degrees of freedom it can vibrate in to permit these properties. Various quantum numbers, like spin and flavor, could correspond to different vibrational modes of the strings, and as a macroscopic example, you need a physical dimension to describe momentum or speed, but you could use multiple dimensions, and none of the normal 3 are the ones specifically and only used for momentum. This framework helps to explain why particles like electrons and protons have specific, unchanging properties. They are like notes in music, if you like. The strings that make up these particles vibrate in a specific way, and those vibrations correspond to fixed values for things like mass, charge, and spin. This discreteness is a hallmark of quantum mechanics, and string theory offers a way to understand it in terms of fundamental strings and their vibrations. For all of its elegance, which is debatable, string theory has some serious challenges. The most glaring problem is the lack of experimental evidence. Despite decades of research, no one has ever detected a string or observed the extra dimensions that string theory requires. Given that string theory is a theory of gravity, and gravity is trillions of times weaker than any other force, it makes finding its interactions to test string theory rather difficult. This is also partly because strings are thought to be incredibly tiny, on the order of the Planck length, which is far smaller than anything we can currently observe. Indeed, a Planck length is to an atomic nucleus what that nucleus is to a planet. The extra dimensions, if they exist, are so compact that they are undetectable with present technology. I should also note that at these scales, the energy of any photon we send to look at something is so high compared to the scale involved that it's like trying to read a microscopic circuit board by shooting it with shotgun pellets, or even atom bombs. It doesn't tend to work well. That still doesn't mean they exist though, and in science you have to be able to provide evidence, or at least a strong implication. We might be able to detect the bottom of a Kaluza-Klein tower, which is the series of states or modes that arise when a physical field is considered in a space that includes compact extra dimensions. Essentially, if you found a particle with a given set of quantum numbers and interactions, charge, spin, etc., and then found another with the same quantum numbers and interactions, but at a multiple of its mass, and so on, that would be a pretty strong indicator these extra compactified dimensions existed. Even this would not be strong evidence string theory, or any specific version of it, was correct though. We would also say string theory is not yet a complete theory. While it provides a framework for understanding the fundamental forces, it doesn't make specific, testable predictions. That doesn't make it wrong, just metaphysically irritating and inconvenient. In science, a good theory is one that can be falsified. That is, it should make predictions that could potentially be proven wrong by experiment. String theory, as it stands, does not meet this criterion. Instead, it offers a vast landscape of possible universes, which makes it difficult to determine which version of the theory, if any, applies to our universe. This brings us to another major criticism of string theory: the landscape problem. String theory predicts an enormous number of possible universes, or vacua, each with its own set of physical laws. Something like 10 to the 500 of these vacua may exist, as we mentioned earlier, each with its own universe. However, this makes it difficult to use string theory to make precise predictions about our own universe, since you should always have a vacua that met the actual conditions of our universe and could then just say that's the one we live in, and thus the theory is true. In some ways, string theory is too flexible. It can be used to describe almost any set of physical laws, which raises some questions about its scientific validity. And again, there aren't a lot of options for testing it. One Jonathan raised while we were drafting the episode ends up requiring a super collider so big and powerful we would need a star larger than ours to run it, an F or maybe even A-type star. Of course, a civilization might well be willing to do just that a millennia or two down the road, and it's not like you're sacrificing the star, just using most of its power to run that collider occasionally and for brief intervals. One of our themes for 2025 is thinking on what post-scarcity and advanced Kardashev-scale civilizations would do with their immense might, and this could be one such example. Nonetheless, it is an attractive theory, or theories. Beyond letting us fix the disconnect between quantum and general relativity, it opens the door to different types of multiverses, which may be reachable, a reason for the Big Bang, for why gravity is so weak and only attractive, offers us some dark matter candidates not available under the standard model, helps smooth out problems with singularities and point-like objects, and some interesting ideas like supersymmetry and the holographic principle. It is a very compelling theory in many ways, because those are a lot of very irritating problems that standard physics doesn't seem to handle well. Time will tell if it's the right one, assuming we can ever find a way to test it. For now, we are left with a fascinating, if somewhat tangled set of theories that often confuses folks, and hopefully we have succeeded in untangling and unraveling string theory a bit today.